So let's talk about a general case projectile. And this is when an object is launched from the ground, goes up, and then comes back down. Okay, it makes a full parabolic shape. So there's some things that you have to keep in mind whenever you're talking about a general case projectile. Please make sure you understand that the horizontal direction properties are different than the vertical direction properties. In the horizontal direction, it's very similar to that of a horizontally launched projectile, where the velocity in the x direction is constant. Okay, the horizontal component of the velocity will always be the same. In this case, the acceleration in the x direction is still 0, because that's what constant velocity means. Okay, but in this case, you are launching it from the ground and going up. Okay, so keep that in mind. You're going to have to find your VXO by using some trig, and because you're going up from the ground, your triangle is here, so the horizontal component is the cosine of the angle. I like to call the launch velocity VO. Sometimes I'll refer to it as my VR, my resultant. That's the hypotenuse of the triangle. Okay, you're still going to have one equation in the x direction because your velocity is constant. So VXO times t. Please keep in mind when you're talking about the time here, this is the time of flight, and that is the whole path. Okay, in the horizontally launched projectile, it's only half of the time technically, because it's only going from top down. In this case, the flight is the whole thing, up and down. Which brings me to a component of the vertical. Okay, a property of the vertical direction is that this is similar to a vertical launch. Okay, so all of the properties for a vertical launch in the y direction are going to apply to a general case projectile's vertical components. So your max height is where the object stops. Okay, that's what it means when Vy is 0. The velocity in the vertical direction at the maximum height is 0. The time to get to Ymax is half the total time. Okay, so a parabola, you know, is symmetrical. So everything on the left is going to be the same but opposite direction on the right. So if I were to launch something at 10 meters per second, it's going to land at 10 meters per second. Whatever the angle that I launch at is going to be the angle over here. They are symmetrical. All right. So let's try one of the problems. If I have an object that is launched from the ground at an angle of 32 degrees at a velocity of 15 meters per second, how far away does it land? Okay, so the first thing that we're going to do is write down some givens. What do I already know? So that way I can determine what I am missing. So some givens to me: theta, the angle which I launched at, and my launch velocity. If you don't like VO and you want to call it VR to remember that it's the hypotenuse, that's totally okay. Whatever is easiest for you. It's the same thing in my book. Okay, and it's asking for how far away does it land. So if I know it's looking for delta x, and I only have one equation that I can use for the horizontal direction, I need to find these variables. Okay, just like before, I'm going to find the time using the y direction. But I'm going to use equation 3 because I know my properties of a vertical launch, that whatever I start with, I'm going to end with. So my Vy0 is going to be the same as my Vy. Okay, the speed that I launch with is going to be the same as that I land with. How do I find my initial velocities? That's the first question, okay? So now we're going to go back and revisit our right triangle trig. I have Vr and I have theta. Okay, so I want to find my Vx initial and my Vy initial, the component vectors of my launch velocity. To find that, we know this is the adjacent side to the angle. So to find Vxo, I'm going to use the cosine. And to find Vyo, I'm going to use the sine function. Remember, Vo and Vr are the same thing. So my Vxo is going to be 15 times the cosine of 32. And my Vy0 is going to be 15 times the sine of 32. Type that in your calculator to get your values. You get 12.7 and 7.95. We're just going to round to 3 sig figs for both of them, just for fun. Okay. Once I get my individual components, now I can start looking for other things. Okay. The reason why you needed to find the vertical component of the velocity is to find the time. Remember, we said we're going to use equation 3 to find the time, which is this one. Now, there's two ways that you can solve for t. You can use your knowledge of, oh, at the maximum height, the velocity is 0, so I can plug 0 in here, Vyo, -10, and find t. But if you do that, you must double the time, because that will only give you the time of the halfway point, right? Ymax is at halfway. Okay, I like to use my properties of a vertical launch and say, well, if it took 7.95 on the way up, that was my launch velocity, I know it's going to land with a negative 7.95 meters per second once it reaches the ground. Okay, launch velocity and landing velocity are equal in magnitude but opposite in direction. Okay, so combine divide, okay. Once you get to that point, now we can solve for what's actually being asked for in the problem, which is your delta x. And we have that one very fancy equation, the only equation for the x direction. And remember to make sure you plug in the correct values. Remember to look at your the ones that you solved for and check to make sure you label everything. Don't forget to label. You cannot mix and match x and y direction. That is no good. Okay? So there you have it. You have solved for how far away does it land, the range of the projectile.